Good morning, my name is Cristell Maneux. I am professor at the University of Bordeaux, and I will explain this paper about the modeling of vertical and ferroelectric junctionless technology for efficient 3D neural network compute cube dedicated to embedded artificial intelligence. The co-authors are from CNRS LAS in Toulouse, France, NAMLab in Dresden, Germany, Global TCAT Solution in Vienna, Austria, EPFL in Lausanne, Switzerland, and INL, University of Lyon in France. In the context, I will explain the need for an efficient simulation tool for vertical gate-all-around junctionless nanowire transistor and associated 3D logic cells, as well as for enhanced functionality using ferroelectric FET and reconfigurable FET for neural network conceptual perspective up to system level. In the context of the fourth industrial revolution, we faced unprecedented growing demand for neural networks, but technology solutions still rely on transistor inherited from the Moore's law, optimized for fundamental machine, which energy efficiency is limited by data transfer between memory and the computing cores because of their 2D implementation schemes. This is a crippling limitation for neural network efficiency. On the contrary, we know that ideal hardware for NNs should feature planes composed of k levels of n times n cubes, each cube being configurable 3D NN compute cell, that is N2, C2, targeting element-wise matrix multiplication, including flexible means to call coefficient from non-volatile memory and for data routing to subsequent layer. The ideal N2C2 structure should take into account the number of inputs, that is the possibility to configure the vertical routing of data between layers in both directions, and then synaptic coefficient, that is the possibility to program them in non-volatile memory elements and connect them to the multipliers, and finally the activation function that can be efficiently programmed in a non-volatile memory elements in a coarse-grained logic in-memory approach. So there are numerous modeling challenges ahead to demonstrate the use of disruptive vertical nanowire technology up to 3D NN architecture. This represents various approaches needed all along the value chain. The TCAT structure, the electromagnetic simulation, the compact models, the 3D layout, the cell library characterization, and finally the system-level benchmark. So let's start with this dedicated technology. The vertical nanowire FET technology has a junctionless architecture composed of an homogeneous highly doped nanowire channel patterned into boron-doped silicon substrate. The current flows between silicide source-drain contacts and is controlled by a gate-all-around structure with a physical channel length of 40 nanometer and a gate oxide thickness of 5 nanometer. The technology features nanowire diameter ranging from 22 nanometer up to 50 nanometer with 60 to 625 parallel nanowires. The threshold voltage range between minus 0.2 to minus 0.5 volt. In addition, the subthreshold behavior of the transistor exhibits a 50 to 70 millivolt per decade subthreshold swing for nanowire diameter smaller than 40 nanometer. The vertical nanowire FET compact model is based on a unified charge-based control model for junctionless transport that dissociates the total charge between a depletion and a complementary contribution in accumulation. While this formulation is developed initially for long channel devices, it is adapted to include short channel effect drain-induced barrier lowering and velocity saturation, as well as band-to-band tunneling and gate-induced drain leakage for describing the substratial behavior. Schottky contact formulation at the source and drain access region are also included through thermoionic and leakage current sources in the intrinsic transistor electrical equivalence circuit. The compact model has been calibrated against both experimental and TCAD simulation data depicting good model accuracy. In terms of test structure, the contribution of the interconnect parasitics to the nanoscale transistor is very important. In fact, as you can see in the 3D sketch, the RF pads, the vias, and the gate contacts appear to be over-dimensioned compared to the nanowires. To take into account the 3D interconnects, we used ADS Momentum EM simulator to model an open structure up to the transistor's terminal. The obtained S parameter permitted to decorrelate the series and parallel components at different reference planes and to build a distributed electrical model from the pad to the gate and drain axes. For instance, the pad capacitance value is 20 femtofarad and the gate access capacitance is 7 femtofarad. Additionally, a resistance modeling the leakage between signal and ground pads was added to reproduce the attenuation observed in the measurement. Finally, a very good agreement was obtained between on-wafer S-parameter measurement and model simulation up to 40 GHz. Once validated on individual transistors, the Verilog A junctionless nanowire FET compact model can be coupled with the parasitic netlist, which is automatically generated by the DTCO flow for any logic circuits based on this technology. As an example, the parasitic RC element of a 3D NAND is generated by the global TCAD solution DTCO flow to account for the intra-cell coupling. The resultant logic circuit simulation with the packed list, the transistor SPICE model, and the model parameter set yields an additional delay of 0.73 nanoseconds compared to the ideal scenario, that is when no parasitics is considered. This confirmed that the SPICE-PEX co-simulation method is mandatory when designing more complex 3D logic architecture. In order to assess the performance and density metrics of the vertical nanowire technology, it is important to make accurate estimation of overall circuit structure and inter-device parasitics. To do so, we used an in-house tool to build 3D representation of a small library of representative static logic gates, which are represented here. Two metal layers are visible in pink and blue at the top and bottom respectively of nanowires, green for N-type and yellow for P-type, as well as gate contacts in orange. In these structures, we applied equivalent scaling to balance pull-up and pull-down branches through the number of vertical nanowire channels per transistor, typically 1 versus 3 for N versus P. We also made some assumptions about the physical design which can be seen in the structure. In particular, we use 40-degree routine which enable compact circuit. We also set power and data input-output contacts at the same top level. As an example, we show here the results from part of a transient simulation of a NAND gate loaded with a capacitance varying from 10 to 80 femtofarad under 1 volt supply voltage. The whole simulation, involving several evaluation cycles, are completed in 100 to 20 seconds, demonstrating the successful use of the compact model. The table on the right shows the simulation-based measurements of typical performance characteristics of the library of logic gates using typical measurement conventions for delay, transition times, and transition energy. This measurement protocol is compatible with library characterization necessary to enable logic synthesis of more complex functions. The figures reported here are far from being competitive with the advanced technology nodes. This was expected since the compact model parameters were calibrated on a rather large experimental device. To increase the system functionality even more, we looked into two different additional device types which can be added to the vertical nanowire platform. The first one is the ferroelectric FET. By incorporation of a ferroelectric hafnium oxide base gate layer, a non-volatile storage element can be added to the gate stack of individual nanowires. This can be used as embedded memory in logic element or to store synaptic weights. Here, on the left side, a 3D layout sketch of a compact and low-energy 1-bit adder is shown, which incorporates this non-volatile storage. The second additional element are reconfigurable transistors with electrically controllable polarity. First, let's start with our approach to predictively model the ferroelectric FET behavior within our junctionless nanowire technology. We started from an experimentally measured polarization hysteresis of an hafnium zirconium oxide capacitor with a thickness of 8.5 nanometer. We modeled the hysteresis with a purely mathematical model following the approach of Presack-Miller that assumed that the overall polarization is a superposition of individual dipoles. The model comprises a ferroelectric branch, a linear capacitance branch, and a leakage branch. Fitting to the experimental has been done by various electrical parameters shown here. Time dependence and sub-loop behavior have been also added. The capacitor model was then area matched to the all-around gate area of the junction-left nanowire transistors and tested for memory operation. The first prediction shows that a rather thick ferroelectric layer of 20 nanometer is needed to yield a reasonable memory window larger than 0.6 volt for a program a rise voltage of 4.5 minus 4.5. Reconfigurable field effect transistors are based on electrostatic doping in nanoscale Schottky device with intrinsic channels. By the use of multiple independent gate electrodes, the current voltage characteristics of the device can be selected to mimic either N-type or P-type behavior. Typically, a programmable gate or polarity gate is used to block the undesired carrier type, here at the drain contact in the band diagram. A second electrode, the control gate, is used to steer the transistor as for regular MOSFETs. Electrostatic doping enables a single hardware device to achieve either N-type or P-type switching functionality, and therefore leads to attractive solution for fine-grained reconfigurability, flexible hardware substrate, and dense regular architecture. A very special concept of these reconfigurable transistors arises from the vertical domain. Multiple nanowires can be connected to a common body, enable inherent X-to-1 multiplexing in a single transistor with X independent drain contacts. As long as the single drain contact is programmed correctly, the signal of any of the source contacts can be delivered to the drain or not, depending on the applied signal CG1, CG2, CG3. If the concept is coupled with a ferroelectric gate layer around the Schottky barrier, the selection of active paths can be stored non-volatile. This way, a flexible reconfigurable input routine between logic blocks can be realized. Here, the concept has been first validated by TCAT simulations. While the previous slide showed the usage of this kind of device in routing application, it is also desirable to consider its application to logic and data processing resources. Work some years ago at EPFL on ambipolar lateral silicon nanowire FET resulted in a generic reconfigurable tile architecture where the various inter-device connections define the actual tile functionality. In this work, we use a non-volatile properties of our technology to make this tile reprogrammable. The use of such non-volatile PCFET in a generic high-expressivity 3D tile-based architecture, as shown on the right, intimately incorporating multi-bit memory capability within computing element is a powerful concept opening the way for a new concept of computing in memory. So, back to the overall picture. Putting all these devices and circuits together, we target the implementation of a flexible computing hardware block for transformer neural networks for machine translation. It is based on the dedicated 3D logic cells library, leveraging the vertical nanowire FET devices and connects through a reconfigurable 3D interconnect frameworks to implement a scalable and versatile 3D architecture model. Its fundamental properties of physical regularity, functional versatility, and in-memory vector processing make it very suitable to explore the hardware-software co-design techniques. For that, the Into-C2 features multiple means of configuration. Firstly, it is function configurable. As a baseline operation, we define a 32-bit integer multiply accumulate function. Secondly, it is connectivity configurable, meaning that it is possible to input from 2 to 8 operands as a number of inputs to each cell. Thirdly, it is coefficient configurable, meaning that it is possible to program synaptic coefficients in memory elements and connect them to the multiplier function blocks. And fourthly, it is data width configurable, meaning that it is possible to implement both intra into C2 scale down and enter into C2 scale up. As shown from the recent paper from Dice et al., the parallel execution of this operation, as we do with into C2, effectively reduce the runtime. Moreover, even with a 16-way parallelism, their execution still represents the lion's share of the runtime. Indeed, the computational patterns of NN's application exhibit a high level of regularity, showcasing compute-intensive hotspot, for the most part embodied in matrix-matrix or matrix-vector multiplications. Matrix-matrix multiplication consume between 66 and 90% of the runtime for a BERT transformer NN, as shown here, thus requiring an efficient and dedicated support, especially in the light of the ever-increasing complexity of NN models. I hope that this presentation has convinced you that dedicated and efficient technologies and design flow architectures for NNs required suitable simulation software tools to explore hardware-software co-design techniques. Thank you.